Okay, in today's lesson, we are going to learn about linear and nonlinear functions. You're going to be able to tell when you have a linear function and when you won't. Your table of contents needs to be filled out. You're going to be attaching your note sheets to page 87 and 88 today. A linear function is a function that will make a straight line when it is graphed. The word linear does have the word line in it, so that's one way how you can remember the definition of linear. An equation is linear if it can be written in this format. This should look familiar to you. Y equals mx plus b is the equation that we used when we learned about graphing earlier in the year. M is your slope and B is your y-intercept. When you go to graph a line, you will have a starting point, which is on the y-intercept, and you will have movement, which is the pattern between the rising and the running of the slope. If you're working with a table of values, you're going to know it's a linear function if you see a constant rate of change throughout the entire table, and we'll practice seeing how that works out. When you're given an equation, what you can do is you can fill out a table of values to create the graph. Then you can look for any patterns among the function that's linear and those that are not. So one of the things we can do when we're working with a function is we can take a table of values and we can calculate your y values based on x values that you sub in. So we're going to substitute this -2, and if -2 goes in place of x and we square it, we get +4. Plus 1 more is where we got the 5. -1 goes in, -1 squared is 1, plus 1 more is 2. 0 gets plugged in, 0 squared is 0, plus 1 is 1. 1 squared plus 1 is 2, 2 squared plus 1 is 5. So once you have your table of values, you will go and you will plot the points. So there's my first point, -2, 5. There's my next point, -1, 2. 0, 1, and then +1, 2, and then +2, 5. This function is not linear because if you connect your points, you will see that they decrease first and then that they increase. And if we were to continue this pattern, we would see that it increases in this direction. Next year, you're going to study this type of graph quite a bit. They're called quadratics or parabolas, and they are not linear. So at the bottom of the page, it asks if it's linear or not, and you're going to say no because it does not form a straight line. Next example, you're given y equals 1/2 x. This equation reminds us that whatever x value you were plugging in, we're going to take 1/2 times the value of that. So 1/2 of -4 is -2, 1/2 of -2 is -1, 1/2 of 0 is still 0, 1/2 of 2 is 1, and 1/2 of 4 is 2. So if we take our values and we plot them, we're at -4, -2, we're at -2, -1. Get rid of that little dot there I made by mistake. Let's see, we have to go to 0, 0. We have to go to 2, 1, and I think already you can tell we have a consistent pattern throughout. If you look, we have a slope of 1/2 where each set of points, if you rise 1 and run 2, rise 1 and run 2, there's that consistent pattern or rate of change. So for this function, we do have a linear pattern because it forms a straight line. What I want you to notice about what's different about the functions in the questions 1 and 2, this one is set up to just be y equals, and then there's a number in front of x. This one has x squared, and what you'll notice is a linear function will never have an exponent up here. A linear function is just going to sometimes have this coefficient attached to it. So what we'll do is we'll just kind of put that information in our notes so we have it. Linear functions do not have x raised to an exponent. There we go. Now, on the next page, we're going to practice some more. I've already taken the x value and I've plugged it in, and you can see at this time we're taking x to the third power. So remember that means -2 times itself, so that's where we get -8. And then if you look at your scale, your x-axis goes by 1s, but your y-axis goes by 2s, so you have to be very careful plotting these points. There's the point -1, -1. There's 0, 0, there's 1, 1, and there's 2, 8. And what you'll notice about this function is it also is very curvy, and that's because it is not linear. X is raised to an exponent, and that creates the curve, and that creates something that is nonlinear. Now, for question 4, we're going to take a look at our point values. This again is found by taking your x values, plugging them in. In this case, we multiply by 1.5 and then we add 2. So each of these x values has been substituted in, and we're going to take a minute to plot those values. -4, -4, -2, -1, 0, 2, 2, 5, and 4, 8. What you'll notice with this one is we have that consistent rate of change again. So when you see that you can draw a perfectly straight line through, you have a linear function. It's also in the format y = mx plus b. There's no exponent on x, and that's what creates the linear function, the straight line. This one is different also. We've got our y equals. We have a number attached to x, but it's attached differently. In this case, we have to take 12 divided by the value of x. So when we divided by 1, we got 12. We divided by 2, we got 6, and so forth. So visually, if we take this and we plot our values, we should be able to tell if it is linear. And even though it started out looking promising that maybe these points were going to line up, we find out quickly that there is a curve to this function also. And as soon as you end up with a curve, remember it is not linear. Linear is meaning they have to form a straight line, or they're in the format y = mx plus b. So we did not have a linear function for the first one. It was raised to an exponent. We did not have a linear function for the third one because of x being in the denominator. Number 6 says, what differences did you notice? And that's what we were just talking about. A linear function does not have x raised to an exponent, and you will not have x in the denominator. You're looking for that format y = mx plus b. Number 7 says, what differences did you notice about the tables? One of the things about the tables you might have noticed is that the tables that didn't have a constant rate of change the whole way across were not going to be linear functions. To summarize today's lesson, looking for equations that are linear, you're going to look for this format, y = mx plus b. That's the first note sheet that's going to get folded in half and put into your notebook. But to finish the other side of your notebook, I would like you to try some examples on your own. You're going to pause the video. When you're done trying these examples, you're going to go through and check your answers. Okay, checking your answers on the sheet that is after the initial notes. You have the first one, which is nonlinear because you're taking x to the third power. Anytime you have x to some exponent, it creates a curve in the graph, so it is going to be non-linear. Number 2 is linear. You're in the format y = mx plus b. There's no fancy exponent here, and it is in the format that we're looking for. So number 2 is linear. Number 3 is nonlinear because what happens is your x is in the denominator, and that creates a curve in the graph. Number 4, we can visually see a curve, so it is nonlinear because you do not have a straight line. Number 5 is perfectly linear. It is going to get lined up with a ruler perfectly, so if it forms a straight line, it is linear. And number 6 is linear. Even though the line is headed downhill, we have a negative slope, it's still linear because the points form a straight line. Number 7 is linear. If you look carefully, you have a constant rate of change between your points, and you might not see it right away because this has you decreasing 15. This also has you decreasing 15, and this also has you decreasing 15. The change in x has you going up 3 each time. So remember, when you're looking at constant rate of change, you want your change in y divided by your change in x. And when that rate is constant all the way across, like ours is, we know it is a linear function. You're going to get that perfect slope where the points get connected over and over and over again with the same pattern. Number 8 does not have the constant rate of change. Here we're decreasing by 1, then we only decrease by a third. On the top, we have a consistent change in x of 5. So if we don't have the same amount of change between the y's and the x's the whole way down the table, it is nonlinear. Number 9 is nonlinear also. You have the temperature that's increasing, but then it starts to level out. And as soon as you don't have that same increase of rising and running the same amount to form a perfectly straight line, if you could connect it with a ruler all along the one edge, it's linear, and this of course is not because we do not have the straight line. Number 10, you have the height of the softball that Hallie threw into the air. You have an increase of 7.2, and then you definitely do not have the same increase of 7.2 as you continue up through this column. This column has a constant rate of a half of an increase each time up, but again, because this does not have the same constant rate of change, we know it's going to be a non-linear function. Make sure you fold both papers in half, tape into your notebook, and we're set.